So in this screencast, we're going to be looking at Newton's second law, which states that the sum of the forces acting on a body of mass m produces an acceleration a. And we can illustrate this by having a mass m sitting on a table. And this table is smooth, but then it starts to get rough, like that. And this friction here is 0. Little f represents friction. The body is mass m, and it's given a push, given a velocity v, and then it starts to hit this rough area here where we say that there is friction. And so friction is measured by defining a coefficient of friction, mu k, k being kinetic friction. There's also a static friction, which we're not looking at in this case. And we give it a push, it's moving with a velocity v, and eventually it comes to a stop, and the final speed of the body is v equals 0. Now, from the time it begins hitting the friction area of the table until the time it stops, we're going to try to determine for that the distance it takes to stop. This would be a problem where a car, you jam on the brakes and the rubber of the tire has friction on the cement of the road, and eventually the car skids to a stop. So it's a practical problem. In that sense, we're going to just solve it for this simple case of a mass moving on a table. So in order to solve this problem, we have to apply the second law in 2 dimensions. 2 dimensions because one dimension in the x direction is motion, but there's also weight acting, or gravity acting on the mass, and there's also a normal force, which is a force table exerts on the mass. So we'll talk about those as we write them down. So the first is the sum of the forces in the x direction, and those are, and this is now when it hits the friction area, because that's the part we're interested in here, the distance it goes. And so when it hits the friction area, there is a force that acts in the negative direction, force of friction. Negative direction meaning because the car slows down, so there must be an opposing force that makes it slow down because the motion of it is to the right. And so we call this force negative, the force of friction, and that's the only force acting. So the sum of the forces equals that, but then the law says that must equal ma. So we set that equal to ma sub x. Then we sum the forces in the y direction. Now in the y direction, there's a force down equal to mg, and there's a force up that the table exerts on the mass to support the mass called Fn, or the normal force. And so now if we write those, Fn, the up direction is taken as positive, so it comes out plus, and the down direction is taken as negative, so minus mg. And since there is no acceleration in the y direction, we say that this equals 0. So that's the application of the law. Now in this case, we have 2 equations, and we have to find a way to express what little f is, and we have to solve for d, and we have to solve for a. So we have like a lot of things that are not known here. So we can't just solve for d directly from this first equation. We have to use the second one to solve for d in the first one. So we're going to define little f, or f, little f, the force of friction. It's defined as the coefficient of friction times the normal force. So this tells you that if the body is heavy, the friction will be greater. If the body is very light, it'll be easy to push because the friction force will be less, even though the surfaces are the same. So you can have a box on a surface, the box is filled with stuff, it's heavy, the same box is not filled, it's light, the light box will be easy to move because the force of friction will be less. So the second equation tells us that the normal force is equal to mg, which we can put in there. And so we know that Fn equals mg. And so we substitute that in there, and we're left with this equation that the force of friction, which is equal to mu k Fn, is actually equal to mu k mg. And that this force of friction is equal to ma. So we're now going to set the force of friction, which is negative in this equation. We're going to use this equation right here. D is not part of that equation. D comes from the distance that's labeled. And so little f, force of friction, is mu k mg, and it's negative, and that must equal m a sub x. And you can see that the m divides out in this case, and we have that the force of friction, rather that the acceleration a sub x is negative mu k g. Now from kinematics, we know that there are equations that relate acceleration and speeds and so on. So we know, let's write down what we know in this equation. In this situation, we know that the initial speed is 10. We defined it as having an initial speed, or we did not, but it should have been there. 10 meters per second is the initial speed. And the final speed is 0 because it stops. Now, you say, well, I pulled this 10 out of the hat. Well, this is just given in the problem. This is a given part of the problem, which I forgot to put down when I first wrote it. So I didn't just make it up. I did make it up, but it should have been there from the beginning. And so when I know these two things, and I know A, and I'm looking for D, then the equation that comes to mind immediately is something you should have written on a 3x5 card, all the equations of kinematics, so you can immediately apply them, is this one, which we've derived, and we know where that comes from. So we put in the values into this equation. We get 0 minus 10 squared equals minus 2 mu k g d. And now I don't think it's very far to go to solve for d. So let's do that right down here. We'll get minus 100 equals 0.2 times 2 is 0.4 times 10. G is a given constant. So that's minus 4 d. Or d is equal to 25 meters. And that's the solution of the first type of problem that you encounter when you solve for friction problems.